In this module, we're going to start to review the basics of convolution. This is part one, and then there'll be another video for part two. So the first thing we need to do is review the concept of what a shift invariant system is. So consider a system where we have the input is a Dirac delta function, and the impulse response is h of x. So the system is shift invariant if I come in with another input, which is a delayed version of the Dirac delta. So this would be a Dirac delta located at 2. So it looks something like this. Okay, whereas this Dirac delta is located at 0. And if the system is shift invariant, then the impulse response to the shifted input must be just a shifted impulse response of the original shifted version of the original impulse response. So then we could write it just as h of x minus 2. Similarly, if we came in with a shifted version that shifted even more, so this would look like this, 0. So it's located at x equals 4. And so therefore, this impulse response, if it's a shift invariant system, must just be the original impulse response shifted by 4. So in general, for a shift invariant system, recall that previously we talked about impulse responses having a dependence on xi, and in this case we're saying that h of semicolon xi just must be a shifted version of some original impulse response, h of x. And so if this holds, we can say that the system is shift invariant. So this is for a 1D example. We can also look at a 2D example. In this case, recall previously we said that impulse responses could depend on the location of the delta function at location xi and eta. And in this case, we're saying that if it's a shift invariant system, it must be such that we just shift the impulse response by xi and eta. This is an example here below where we have an impulse response and we have its corresponding response function. And here we've shifted the impulse response down here. And if it's a shift invariant system, we've simply shifted the delta function down here. If it's a shift invariant system, then we simply shift the impulse response down to here. And everything else is the same. It's simply a shifted version of the original impulse response. So now we're going to combine the two concepts of linearity and shift invariance together and form what's called a linear shift invariant system. So this is going to allow us to write a very nice expression for the response of any linear shift invariant system to any arbitrary input. So as an example, let's take this input here where this is an input, let's call it, we call these x's. Let's see. Let's call this g sub x, and it's got a delta function at the origin plus 2 times the delta function at 1 plus the delta function at 2. Okay, so that's what that function looks like. And here we have the impulse response. So this is the response to this impulse at 0. All right. So far we've just defined things. Now we're saying what is the response of our input to this, of our system to this entire input. So the first impulse, it gives rise to this response. The second impulse, because of shift invariance, it's a shifted version. And then because of the scaling property of linearity, it's just multiplied by 2 because this delta function had a weighting of 2. And then the final one is the response to this delta function. And because of shift invariance, it is simply a delayed version of the original impulse response. And since this has a weight of 1, there's just no weight out there. It's just implicit 1. So far that's the shift invariance, and we've also used a scaling property for linearity. And then the additional property says that we can simply take all these responses and add them up. And so in this case, we might get something like this as the response. All right? So that's an example of a linear shift invariant system. It's where the output is the weighted sum of the shifted impulse responses. And so that's key. With the shift invariant system, you can simply use shifted impulse responses. Okay, so let's look at an example of this where we have, we'll revisit our discrete time example from before. So remember before, in a previous module, we had 1, 2, 1. And here we're using Kronecker deltas instead of Dirac deltas just to keep things simple. Let's locate at 0, 1, and 2, index of m. Okay, so once again we have g sub 0 equals 1, g sub 1 equals 2, g sub 2 equals 1. All right, and remember before we said that in our previous example we had g sub m giving rise to some impulse response, and I think it looks something like this: 1 and 2. All right. Now in this case, we consider the impulse response to a shifted Kronecker delta, and due to shift invariance, it must be simply a delayed version of our impulse response. Okay, of our original impulse response. Similarly, delta m minus 2 is going to be a delayed version, shifted by 2. All right, so this is h of m. This is h of m minus 1, and this is h of m minus 2. All right, and similar to before, we simply take each of these, we weight them, so we multiply by 1, multiply by 2, multiply by 1, and then we're going to take all of these and sum them up. And so let's see what happens when we do that. So the first one is 1, 2, 0 and 1. The second one is we add on, we take this and multiply by 2, so we're going to have 2 added here, and then 4 added here. Okay. And then similarly for the last one, we're going to take this and multiply it by 1. And so we're going to add 2 here, and it's going to be adding 1 here, and then 2 here at that m equals 0. Okay, so when we do all that, our output is going to look something like this. We're going to have, this is 1 here. So 1 here, 2 plus 2 is 4. That's 4. 4 plus 1 is 5. So we're going to have 5. And then we just have this 2 over here. Okay, so it's locations 1, 2, 3, and 0. All right. So once again, we've got our final output is simply a weighted sum of impulse responses. But the key here is the impulse response is all shifted versions of some initial impulse response like that. All right, so that's basically the intuition behind convolution. Now here, what we have is the writing this out using sort of more abstract notation. So this is the same thing we had before, but we're going to keep everything here in abstract notation. And what we're going to look at is the output, the response of the linear system to this input. And now the L is both linear, which we looked at before under superposition, but it's also shift invariant. All right, so here we just have our linear system and we're putting this input here. So it's a weighted sum of Kronecker delta functions. Due to linearity, once again, we can split it up into the sum of the individual responses. And once again, due to linearity, we can factor out the scaling terms. Okay. And so now the only difference here from what we did with superposition is the linear response to each of these shifted delta functions are simply shifted versions of the original impulse response. Okay. And so here, what we end up with is we have these shifted impulse responses. So these are shifted impulse responses. And then we also have our weights. Okay, so it's a weighted sum of shifted impulse responses. Now, in continuous space or continuous time, we replace the summation sign with an integral sign. And so here, what we're seeing here was the general expression we saw before for superposition. Now we replace this with shifted versions. And so this is a shifted impulse response weighted by the appropriate weight. And then instead of summation, we integrate. Okay, but the intuition is still the same. It's essentially a weighted sum of shifted impulse responses. And this form comes up so often we give it a special name. We call it convolution, and we typically denote it with this asterisk symbol. So this would mean that G is convolved with X. Okay, so this operation of taking G, multiplying it by a shifted versions of X, and then integrating over all of space is what's known as convolution. Okay, so in a subsequent module, we'll look at sort of how to do the mechanics, but let's just go over it a little right now. So if you look at what's in this integral sign, we have g of I and g of x minus I. Okay, so this minus thing means we have to flip our function, and then this x means we're going to shift it. And we'll take a closer look at that in a later module. Then we multiply these two components, and then we simply integrate that multiplication. So we're not going to do too many difficult examples of that, but we will do some of that in a later module. For this module, I just really want to focus on an extremely useful fact, which is if I take any function g and convolve it with a shifted delta function, the output is it simply shifts my function to the location of that delta function. Okay, and you can get this from the sifting property, but for now, this is just something that's very useful to commit to memory. And let's do a couple examples to sort of